So yeah, so feel free to interrupt me, but so keep in mind I am recording. So yeah. Okay, all right. So the first problem is we're assuming that x is normal with mean 2, variance 10 squared. So we sample the variable x once. So now what we want to know is what is the probability of x being between 2.1 and 3.1, right? So when we're saying that x is normal, so I believe it's like 2 and 10 squared, yeah? So when x is normal to 10 squared, so 10 squared is the variance, so that means that the standard deviation is going to be 10. So what things look like is kind of like this. So this is going to be 2. And then the standard deviation is 10. So that's going to be pretty wide here. So this should be the highest point, actually. And now what we want is we want the probability between 2.1 and 3.1. So this is 2. So this would be 2.1, let's say, and 3.1. So we want the area that's between this. This is going to be the probability of x ending up between 2.1 and 3.1. So one way to do it is to say, we'll just compute the area up until 3.1, and then we'll subtract the area that's up to 2.1. So this would be p norm. So p norm is the area under this curve up to 3.1. That also means that's the probability of x being 3.1 and less. And here we need to specify the mean. So the mean is 2, and we specify DSD. So DSD is 10. And then we want to subtract p norm of q equals 2.1, mean equals 2, SD equals 10. So this would be the solution. So we can just type it in.
For this problem, is it 3.1 inclusive or exclusive?
Well, so because that's a good question. So because it's a continuous distribution, like we said, the probability that it's actually going to be exactly 3.1 is 0. So it doesn't matter. It's the same.
Okay.
So for discrete distributions, when you say p norm q equals, then that's inclusive of 3.1. But here it doesn't matter. So we'll say mean is 2, SD is 10, and we'll subtract p norm of 2.1, and that comes out to, I have a minus there. So I'll just delete that. And that comes out to, okay, so 4%. So now we want to do it a different way. So the question now is, we want to get the same thing, but we need to use p norm with mean equals 0 and SD equals to 1, right? So the thing we'll use here is that, so we start with x being normal to 10 squared. And what we know is that x minus 2 divided by 10 is normal 0, 1, right? So what we want to say is, what's the probability of 2.1 smaller than x minus 2 divided by 10, smaller than 3.1? And so, sorry, not like that. So this is x, of course, smaller than 3.1. So that's what we want. So now we'll transform 2.1 and 3.1 in the same way. So that's going to be equal to p of 2.1 minus 2 divided by 10, smaller than x minus 2 divided by 10, smaller than 3.1 minus 2 divided by 10. And this we can compute using p norm. So this would be p norm of this minus p norm of this with mean 0 and SD1, because this thing is N01. Okay, so that means that that's going to be, so P norm, so Q is 3.1 minus 2 divided by 10, mean is 0, as D is 1, minus this, and this is going to be 2.1 minus 2 divided by 10, mean is 0, as D is 1, and that's exactly the same thing. Okay, so now we probably need to do it with R norm, right? So yeah, so now we want to use R norm, and we're allowed to use R norm kind of however we want. So what we'll do is we'll say, okay, so we need to basically generate data from the original distribution, mean 2 as D10, and say how often do the x's fall between 2.1 and 3.1. So I'll say x is R norm, and here this is like as many as they want. So the more samples they generate, the more accurate the estimate is going to be. So R norm this, and we'll say mean is 2 and SD is 10. And now we want what proportion of the x's out of those 10,000 x's, what proportion falls between 2.1 and 3.1. And here your question from before actually makes sense. Like, do we do like smaller equal or do we do smaller? And here, well, we can like technically, so with P norm, we really couldn't have done anything. But here we can look at what we're actually being asked to do. So here we're asking strictly smaller. So for R norm, we'll use strictly smaller. Again, kind of, it's never going to be exactly 2.1, 3.1, or almost never. So it's never the case here, I'm sure, that x is equal to 2.1. And it's never the case that it's equal to 3.1. So whether it's smaller or smaller than equal is just not going to matter. So we are doing mean of, so x needs to be both greater than 2.1, and it needs to be smaller than 3.1. So this is a bunch of trues and falses. It's only ever true if x is between 2.1 and 3.1, because it needs to be both greater than 2.1, smaller than 3.1. And here we'll get the answer. So with 100,000 samples, we got 0.0406, which is not quite right. So if you increase the number of samples, you likely will get something that's a little bit closer. Although in this case, we actually, no, yeah, so this is a little bit closer still. Okay. So problem 1D is asking us to compute the same thing, but with so the same thing, but with R norm mean 0 as D1. So it's the same trick as before. So we'll just do x is R norm, and we'll do like whatever, 1 million. And here we'll say mean equals 0 as D equals 1. So you'll note that this is not actually necessary. So you could just say R norm n equals 10, and that'll give you variables with mean 0 as D1. But we're still doing it like that. And now we'll do the same thing. But now we want to say that x is greater than 2.1, the transformed version. So now let's do something different. So we could have done, well, we'll do it first like that. So we could have done 2.1 minus 1 divided by 10, and 3.1 minus 1 divided by 10. And that works. Well, should work. 3.1 minus 2. Okay, so that works. But another way of doing it is, instead of transforming the boundaries, we can transform x. Okay, so the trick that we can use is the reverse trick from here. So we can say, if y is n01, then 10y plus 2 is n to 10 squared. Okay, So we can do the y, and then this is the same as our x's, right? So that means that we could have done so x is like this, but here we will transform it. So we'll do times 10 plus 2. And once we have that, we can just see whether x is between 2.1 and 3.1. That's going to give us the same result. Okay, so that is problem 1. So let's do problem 2. So here it says, suppose 65% of Princeton students like Wawa better than World Coffee. We selected a random sample of 100 students, asked them which they prefer. What is the probability that more than 78 students said Wawa? And we want to use p-binom for that. So we want the probability of 78 or more when the underlying probability is 65. So 78 or more, that means we need to exclude 77 or less. So we'll do 1 minus p-binom. Q is equal to 77, size is equal to 100, prob is equal to 0.65, right? So this is the probability of 77 or fewer yeses. 1 minus that is the probability of 78 or more, which is what we need. We need 78 or more. So this probability is this much, so not a lot, but whatever. So next we're asked to do the same. So this was 2A. So next we are asked to do the same thing, but with the normal distribution. So what we know is that we can approximate the binomial distribution using the normal distribution when we're using mean as n times, well, so here it would be size times prob in kind of our terminology. In math, we write like n times theta. And variance is prob times 1 minus prob times size. Okay, so that means that the SD is square root of size times prob times 1 minus prob. So instead of writing p-binom here, we'll write p-norm. And for now, we'll keep the Q77. So we'll say mean is equal to 100 times 0.65 is just 65. And SD is the square root of 100 times 0.65 times 0.35. So that's going to be like this. So this is a little bit different. So one issue here is the issue with the continuity correction. So we're not kind of overly concerned with this in this course, but yeah, like if you do it like as 77.5 or something, it'll get closer to what you'd expect. So in fact, kind of 77.9 probably gives like the closest, but we'll leave it as like 77.5. Not too worried about the continuity correction here. It becomes less important when the size of the sample is more than is kind of substantially more than 100. So okay.
Oh, out of curiosity, sorry to interrupt. How many decimal places does the continuity correction go to exactly?
Oh, so like it's not about decimal places. Like it's not going to be constant, right? So like there is like a formula to do it, but like we don't really care. Mm-hmm. So it's not like about the decimal places. It's like there is a number which it's actually really easy to find out, right? So you can just say like, so this is the exact answer, right? So p-binom is this. So you can ask like, what's the exact quantile here? So you can do it with q-binom, q-norm, sorry. So you can specify q is equal to p-binom, right? And then you'd say, so this would be like mean is 65, SD is this much. And like it's not like a super useful exercise. Well, why is it not happy? Oh, because it's P. So yeah, so 77.89, 42 is going to give you kind of the exact same number. Like there are formulas for that, but like don't really care.
Okay, thank you.
Okay, all right. Okay, so that's that. So 2C. So 2C is probably asking us our norm. Oh, there is no 2C. So problem 3. So Harvard and Stanford, worst 60 students said that Stanford is worse. Compute the p-value for the null hypothesis that Princeton students think Harvard and Stanford are equally bad on average. So on average across the students. So how do we express the null hypothesis here? So the null hypothesis is like probability that the person said Stanford. So let's say Stanford is equal to yes, is the worst one, is 0.5. So that means that when asked to choose between Harvard and Stanford, they have a 0.5 probability of choosing Stanford. So now we're asked to compute the p-value for the null. So for the null hypothesis, so 60 students said Princeton is worse. So we need to compute the probability here of 60 or more or 40 or less, right? So the p-value would be the probability of seeing something as extreme or more extreme than 60 as compared to the 50 that we expect, right? So you can do it with p-binom. So we'll say p-binom. So more than 60. So this is again size 100, prob 0.5. And here we want also to add, so this is 1 minus, of course. So 1 minus, and we want to exclude 59 or more. We want to include 60. So here we have Q is equal to 59. And now here I'll say p binom Q is equal to 40 or less. So we just say Q is 40 and size is 100 and prob is 0.5. So the p-value is this much. So it's slightly more than 5%. So if we're using if we pre-committed to using 5% as our threshold, we're going to say we don't have evidence that there is a preference among the subjects of the survey about Harvard versus Stanford, right? So it could be 50%. We don't have strong evidence against that, although we have evidence that's kind of suggestive. So like a difference of 60 versus 50 is large enough that it's almost significant. Okay, so that's that. So problem 4 is answer problem 2 using only R norm with mean 0 as the 1. So what do we want to do? So we want to generate samples, from this distribution, which are kind of going to be like the number of answers that are Harvard, for example. So again, so the mean here is going to be 50. The SD is going to be square root of 0.5 times 0.5 times 100. Which is, so that's convenient because 0.5 times 0.5, square root of that is 0.5 times square root of 100, that's 10. So the standard deviation is going to be 5. How do we generate numbers that are between 0 and 100 that are representative of like approximately the number of yeses? So we'll use the trick from before where we'll say our norm, and here we're going to say, so we have 100 responses. So we got to say mean is equal to 0 and SD is equal to 1. But what we can do is we can multiply by the standard deviation and then add the mean. And those would look like samples from a normal distribution with mean 50 and standard deviation 5. So this is the same trick that we used before, this one. So, okay, So that is the answers. Let's pull. So by the way, we don't need to say 100 necessarily. So kind of as many as possible. So this is like the number of yeses, right? So now what we want to know is under this null hypothesis, how many are greater than greater or equal than 60 or small or equal than 40. So here we might consider rounding so that we don't worry about like fractional votes, because the poll thing, it looks like this, right? So those are like not like number of yeses. So we can round using round. So the poll is going to be like this. And now we can say, what's the probability of poll greater or equal than 60 or poll smaller or equal than 40? And we got 5.7%. This was very close, 5.68. Okay, so that is problem 3 of the Precept. Save it. Oh, actually, don't need to save it. So this is P8. Okay. Okay. Oh, okay, that was wrong. Just 1 second. So I do want to stop recording.